We have about 40 minutes, I guess, to describe a little bit of our project. Can I start?
Please go ahead.
Okay. So there are two parts. I will talk about the theoretical side, and Simon will talk about what is implemented or what we are implementing right now. Maybe it's good to know that I'm a mathematician. I have always had a strong interest in mathematics. In logic. I always appreciated the precision and the clarity of logic. I've been trying to apply it to modeling and to knowledge representation since my PhD, basically. In the end, we came up with a project which is running now for perhaps 15 years or so, 20 years, which we call the F.KB project, with an exciting fundamental research question, which is basically the good old knowledge application and reasoning research question. And we possess, human experts possess declarative knowledge, and we use it to accomplish tasks, to solve problems. We want to understand how this works. It's inherently a knowledge representation and reasoning research question, and I think that if we ever want to be able to build software systems in a principled way, we will need to understand more of this question than we currently do. In any case, it places the field of knowledge representation at the foundations of computer science. If you look at the state of the art, then we see that about every area in computational logic, declarative programming paradigms, many fields of symbolic AI, modeling languages are involved in aspects of this basic question. It seems to me fair to say that scientific understanding is partial and that our understanding is scattered over the many fields of computational logic. There is no systematic scientific theory or research programming, in my opinion. And as a consequence, we still understand not enough of this. If you look at the field of computational logic, it's extremely broad and heterogeneous. We have all these different kinds of logic: classical logic, deductive databases, logic programming, answer set programming, abductive logic programming, constraint programming, etc. With all these different forms of inference that these logics implement, it's always my impression that there are so many overlaps there. There are so many different syntactical styles, language constructs. Perhaps an excessive importance is attached at syntactic hubris. And often different terminologies and conceptuologies hide overlaps between different languages. When we peek through the surface, I think very often we see overlaps between all these different languages. One issue that is probably more responsible for the fragmentation than anything else is the aspect of the reasoning task. All these different logics on my previous slide are involved in other forms of inference. Now, being a mathematician, I always thought that declarative knowledge was supposed to be independent of the problem. So declarative knowledge is about information, and it's not about a specific form of inference. You should be able to reuse the same knowledge for different types of tasks and computational tasks. So there have been this. We have had this effort. We've done this effort to, let's say, separate knowledge from the reasoning, and basically build a knowledge-based system for a rich knowledge representation language. Because we feel that this separation has sometimes leads to remarkable gaps in our understanding of inference. And I have here a small illustration. Take a simple graph coloring problem. How could we solve that in a declarative way? If you think about the knowledge that is available, what is the available knowledge? I think it's fair to say that the central piece of knowledge is just this one proposition, namely that different adjacent vertices do not have the same color. We can express this in first order logic by this kind of statement here. Now, if you want to solve this kind of this proposition to solve the graph coloring problem, you will of course have to add input. And the input will consist of a graph, also a set of colors. And from that we want to obtain the output, which is a function, a value for the call function, which together with the input satisfies this axiom. I think that's very obvious, but what kind of inference do we need to solve this problem? Well, we are using in first order logic. First order logic is typically viewed as deductive logic, but obviously deductive reasoning is not going to help us here. So we need another form of inference. We probably need something like model generation or model expansion. Now, you can see that the question that I posed here, what kind of inference do we need to solve the problem? It's a type of question that until fairly recently was not even asked in the context of classical logic. Because classical logic was always seen as the study of deductive reasoning, and if you look at Wikipedia, you will still find that classical logic is about deductive reasoning. Deductive reasoning doesn't help in solving the graph coloring problem. We need here other forms of inference. But these other forms of inference were studied in other areas of computational logic, in particular constraint programming, but now also in answer set programming, if you're familiar with that. So something is going wrong here, in the sense that the representation of that basic piece of knowledge here, it is really essentially a first order logic, but because we are partitioning our logic together with the inference, we miss certain essential aspects here. So what if we could bundle what is known about knowledge representation and inference in one coherent scientific framework in which the knowledge is separated from the reasoning, so that we could reuse the same knowledge for different problems? And so that is the aim of the FLDOT project, the underlying idea. It's an integration project. On the logical level, we develop this language FLDOT based on essentially the hypothesis that knowledge exists and it can be studied through the methods of formal empirical science. And we do our best to develop a language in which all the language constructs are well motivated and well argued to be expressing certain types of declarative knowledge. We focus on expressive natural languages. So I say here a language rich enough so that the information that is relevant to solve a problem can be represented. This is not always the case. For example, if you look at a field like description logic, they impose very strict restrictions and expressivity with the aim of building efficient theorem proving. And then in the end, there is a lot of knowledge that cannot be expressed in those logics, and that's something we don't want to do. So we want to have an expressive logic. We want to study useful and precise language constructs of natural language and other formal languages, and we want to integrate them in classical logic. On the inference level, we try to build solvers that offer various forms of inference. Often we use other solvers. For now, for example, strongly use Z3, Microsoft System Z3. And we try to integrate various solving techniques from various declarative programming paradigms in our knowledge base. And on the application level, we're always looking for interesting new language constructs that are needed in new applications, but also in trying to have a better understanding of what tasks and computational problems arise in this field, and what kind of inference we would need to solve them using our declarative knowledge base. So we are always eagerly searching for novel ways of using declarative specifications to solve problems. So that's the introduction to the main principles of our project. I have a few minutes left to talk about the logic FODOT. There's a lot to be said about this, but I will focus on the main components here. So maybe the first thing that needs to be said is, why do we use first order logic as a foundation? First order logic was the outcome of research of long ago, research into the laws of thought by such people like Boole, Frege, Leibniz, Peirce. Why do we think that should be the foundation? Well, for the simple reason that we believe that first order logic is a small set of connectives. They are essential for knowledge representation. And I think they are implemented basically in the right way in first order logic. Maybe for you, I don't know what your interest is. Maybe this could be obvious. But I come from another domain, in logic programming, where this statement would absolutely not be obvious, and many people would believe that first order logic is absolutely not the right language to build a knowledge representation project on. One of the things we absolutely appreciate and we want to continue in our project is that we want a language with very precise informal semantics, and definitely first order logic. We appreciate the precision, the mathematical precision of the informal semantics of first order logic, which is that, for example, here, this statement means all humans are men or women, and there is no vaguity and ambiguity in this. So all our language constructs that we've added to the language have the same sharpness. We think that every interesting modeling language will have substantial overlap with first order logic. On the other hand, it's our experience that for knowledge representation, first order logic is absolutely not sufficient. And so we are developing extensions to turn first order logic into a practical KR language. We need types, we need partial functions, we need inductive definitions, we need aggregates, arithmetic, perhaps also co-inductive definitions. Sometimes we need modal operators, and so on. Okay. So that is our our language framework start from first-order logic, and we extend it in a coherent way with other precise language constructs. I think there is, with the limited time that I have available, I can only talk about one extension, and it's the extension with inductive definitions. So that has a long history for us. I already mentioned I did my PhD around 1990, and in that case, in that time, I was working in a group concerned with logic programming, Prolog. I don't know if you are still very familiar with that language, but in that language, logic programming was seen as a sublogic of classical logic. In fact, the Horn clause sublogic. Very soon after the start of that language, people wrote down little programs like this one here, which is the member program. I hope you're still familiar enough with Prolog to understand this here. Basically, it consists of two rules. The first one says that the head of a list is a member of the list, and the second is an inductive rule saying that X belongs to a list if it belongs to the tail of that list. So when logic programming was introduced, it was presented as a sublanguage of classical logic, and there are still many people in the community that view logic programming in this way. Now, very soon after the invention of logic programming, there were all kinds of problems showing up, and this particular program, for example, unfortunately, the one theory, classical logic theory that corresponds to it, does not entail that, for example, member 1 is not a member of the list 2, 3, 4. People were bothered seriously by this because this seemed like a very nice theory, very natural theory, and obviously 1 is not a member of the list 2 to 4. So it was really a pity that, and problematic basically, that the logic could not derive that 1 was not a member of the list 2 to 4. It took me a while before I really understood what the problem here was. And basically, I understood the problem when I realized that I had not been interpreting this as a Horn theory, but as an inductive definition. If you take this program and interpret it as an inductive definition and augment it with a few extra axioms to explain what recursive data structures such as lists are about, then you can easily prove that this specification entails that 1 is not a member of the list 2, 3, 4. So, for me, that was the start of my research in knowledge representation. I viewed logic programs as a logic of inductive definitions, and I continue to build on that. The view is reasonably well known, but has never been embraced by the entire logic programming community. And at this moment, there are still problems in the field to explain what negation as failure means. Here in my case, it's simply classical negation. What has changed is we don't interpret the rules as material implications, but as rules and inductive definitions. And then inductive definitions entail lots of negative information, and they simply entail what we would like what we would like, namely that 1 is not a member of the list 2 to 4. problem of this view was that at that time, in the 70s or in the 80s, there were not really good theories about inductive definitions. Kind of definitions we could recognize here. Here are two very common types of definitions. One is the monotone inductive definition types. Here is an example. The transitive closure of a graph is defined inductively as follows. Tuple xy belongs to the transitive closure if it belongs to the graph. Another case is represented by the inductive rule. Tuple xy belongs to the transitive closure if for some vertex xz and zy belongs to the transitive closure. This is a simple, nice, elegant, and very common type of inductive definition of the kind that you find in mathematics. Here is another type of definition of a satisfaction relation. You should all know that definition, I guess. It's a definition by structural induction. We define, I hope you recognize the rules, an atomic formula is satisfied in a structure. We are talking about propositional logic here. If the atom belongs to the structure, here is the rule for conjunction. It's a standard inductive rule. And then we have the rule for the negation, which is special. The negation of a formula is satisfied in a structure if the component formula alpha is not satisfied yet. The rule is special because it contains negation in the body. It is actually quite common to find definitions by structural induction that do contain negation in the body. And so this kind of definitions here suggests that there should be a basis for explaining logic programs with negation in terms of inductive definitions that are monotone or that are non-monotone, that contain negation in the body. So both share a similar format. They are informal rules. Some of them contain negation in the body, like this one here. Many definitions contain parameters, so they define concepts in terms of other concepts. In particular, here we define a transitive closure in terms of a graph, which is not defined by the definition. And so the goal now is to collect these ideas and to build an inductive definition logic that covers both types of definitions, and then to use this as a way of expressing logic programs and integrating them with classical logic. So that has been the work that has been done in between 2000 and 2010. We have here a concept, inductive definitions, which is well understood, which is precise, which is an objective, informal language construct frequently used in mathematics. It should be amenable for formal scientific study, and actually it is. And we develop this into logic. There are good reasons to add inductive definitions to first-order logic. They have many applications, certainly in computer science, software engineering applications. We know that inductive definitions cannot be expressed in first-order logic. It's a simple consequence of the compactness theorem, and so it seems like an excellent idea to extend first-order logic with them. And so we have done this. There are actually many studies of various forms of inductive definitions. There actually not one has really the right syntactical format to be able to express the type of definitions that we find in Prolog, or that is suitable to express both the monotone type of inductive definitions and definitions of the well-founded order that we just saw. Okay. So around 2000, I started to argue that some of the semantics that had been introduced for logic programming were suitable as a semantical study of inductive definitions and could be used to build a new logic of inductive definitions. So that led us to the logic FOID, first order logic, extended with inductive definitions. So a definition in that logic is a set of definitional rules. I'll give you a few examples in a moment. So rules with a head, which is an atomic formula with a collection of terms, and then a body, which is the first order logic formula. And FOID theory is simply a set of first order logic axioms and a set of these definitions. And formal semantics was borrowed from logic programming. We used the well-founded semantics and used it to define a model semantics for these definitional rules. Here is a small example. How am I doing in time? I don't hear anybody, but I don't know.
You still have about 11 minutes.
I used how many minutes?
Yeah, it's 10 to 11 minutes.
Okay, I could still use a few minutes to go on here then.
Yeah.
All right. So here is an interesting inductive definition. Actually, it's not. It's an extension. It's written in an extension of FOID because it also uses aggregates. Here is the definition. A company A controls a company B if the total sum of the shares in company B that is owned either by A itself or by some company controlled by A is more than 50%. Okay. It's one of my favorite inductive definitions. It's clearly inductive because you define it's an inductive rule here. And it needs some counting. So how are we going to express this in our logic? We will use a predicate count, which means count y means that company X controls company Y. I will use a predicate owns shares, which is a parameter of this definition, which tells us that company X directly owns S percent of the shares of company Y. Okay, and then using this, we can express with one rule the inductive definition. So let me read it for you. The company A controls the company B if the sum of the shares S is the number of shares owned by a company C, where C is either A itself or a company C controlled by A, and S is the set of shares owned by C in the company B. That sum should be more than 50%. Okay. So this is an almost literal translation of this definition using the sum aggregate. So the sum over all the pairs S and C, where S is the set of shares owned by C of the company B, and C is any company that is either A or that is controlled by A. So that is a kind of inductive definition we can express in our logic. Here is another example. I show it because this example here shows the clear mix of first-order logic with an inductive definition. It's the traveling salesman. I guess you know the traveling salesman. There is a number of cities, roads between the cities. The existence of a road between city X and Y is represented by a predicate, road XY. The start of the traveling salesman is the city A, so that's where the salesman is starting his travel. And the goal is to compute a path from the city A, a path that passes over every city exactly once, and that returns to A. Now, how are we going to solve this? Well, we are going to introduce a predicate n, xy, so n stands for next and represents that after the salesman was in city X, he moves to the city Y. And so for the salesman to go from X to Y, there has to be a road. And this next relation should be a path. That means that there should be only one incoming path in every city and only one outgoing path from every city. Okay, so these are the properties represented here. And then we should also say that each city is reached by the agent. Every city should be reached. You should pass at every city. And then the goal is that we define what city can be reached. Well, since we start from the first city, if our first city that we move to from A is X, then X is reached. And then the second rule is an inductive rule. If we can reach a city Y and we go from Y to X, then also X is reached. So this is a standard inductive definition of reachability. Now we have a theory consisting of an inductive definition and at the same time a theory that states that n is a path that passes at every city. This is the specification of our knowledge. In some sense, you could see here that this is almost like a logic program, except that it has a parameter that is not defined here. So basically here, what do we need? What kind of inference do we need for solving a traveling salesman problem? Well, we need to provide information about what are the cities, what are the roads. And then we search for a model of this theory. A model will return to us a value for the predicate n. So the next relation, which represents the path, the path of the agent. And this path will be a path of the kind that we want for the traveling agent. It will pass at every city and it will return to the city A because also the city A is reached. And that can only happen at the final move in the path. Why did I want to show this problem? Because it contains a few rules that remind us of logic programming. But whereas logic programming can only reason about a program that contains the definition for all its predicates, here we see that we have a theory where we basically know the defined relation. We know what the defined relation is. It's the set of all the cities. Okay. What needs to be searched here is a value for this predicate n, so that its reachability relation is actually the set of all the cities. So this is a completely different form of inference that we need here than the type of inference provided in logic programming. And that is one of our main goals here, to be able to represent knowledge in a way that is independent of the problems, and then to have available, to offer different forms of inference that can solve a broad range of different problems without specifications. Okay, I'll skip this example here. In any case, we obtained this logic f dot. It covers and overlaps with many formalisms in computational logic. Clearly, it extends logic programming, but also answer set programming, abductive logic programming, data log, fixed point logics. And it's the only logic that integrates classical logic with logic programming. I would say it's the only logic that provides a natural, clean conceptual integration of logic programming with classical logic. And that is something that is important from a scientific point of view. It also offers a clean and clear declarative interpretation of logic programming, which is a problem that is basically open for 50 years. So this is a solution for this problem. I'm almost finished with my talk. I wanted to say something by way of introduction for Simon's part. I wanted to explain what was how we view inference. Our view is that we want to use these f dot theories as a knowledge base. And what we want is, or what we need is that this knowledge base offers different forms of inference using which we can solve a range of problems with the same knowledge base. I've illustrated this here with a typical application. Imagine that we want to solve an application for university course scheduling. Basically, our knowledge base will contain a theory of the correct laws of correct university schedules. Will represent that every lecture has to be taught, that it has to be taught, every lecture has to be taught in a room, that no lecturer can be at multiple places at the same time, no room can be used for multiple lectures at the same time, no class can be present at multiple lectures at the same time, and many more of these simple rules. So writing the theory of university course scheduling is feasible. It's something that is commonly done in constraint programming. It can be done in our logic as well. But the point I want to make here is that the same theory is really useful from many different points of view. So to start with, if we want to compute a university course schedule, then basically our problem is going to be a model generation problem. We will have a lot of information, data. We will know what rooms are available, what the time slots are. We will know what classes that exist, what lectures need to be taught, and so on. So that's all data. Basically, we know most of the data, except that we will not know on what time slots lectures take place and in what rooms lectures take place. Okay. So we are in search for values of these predicates such that the knowledge base is satisfied. And we need the model generation inference to solve such a problem. Okay. So scheduling is really a constraint programming problem, but phrased in theoretical terms, it is a model generation or a model expansion problem. But that's not all we can do. Imagine that after a while, a schedule has been computed, has been stored in a database, and somebody performs manual updates to the database. It is of course obvious that the knowledge that we have expressed in our knowledge base is also going to help us to check if the manual updates to the schedule in the database, whether they are correct. We can. But for that, we need another form of inference. And we need model checking for that. Okay. Another type of problem that could arise is that we come with a new constraint. For example, the lecturer of the course logic is not available on Wednesday. His course was scheduled on Wednesday. Now we need to revise the schedule so that the new schedule takes the new constraint into consideration. And we need, again, another form of inference. I call it revision inference, where again we can use that same knowledge base and update the existing schedule to satisfy the old constraints, but also the new constraints. I hope the picture becomes clear. We want this knowledge base written in FODOT to be used for multiple types of problems. And in the past, we have been looking for interesting applications, especially from the point of view that multiple forms of inference could be applied on the same knowledge base to solve a range of problems. So that's the last thing I had to say about this project. And now I suspect that Simon will take over. Thank you for listening.
Hi, Mark. I guess given the time, it's best that we skip my part. But I guess I can always present it at another time point. And I'm sure that people will have questions for you as well.
I think I misunderstood. I had not understood that I was going so far over my time. Sorry for that, Simon. I thought I still have 10 minutes, but actually, yeah, that was probably including your part of the talk. Huh? Sorry for that, Simon.
Yeah, no problem.
Thanks, Mark. That was an interesting talk. We are surely looking forward to Simon's follow-up talk on this topic. But for now, we'll invite questions about Mark's part of the talk. So yeah, if anybody has questions, they can ask Mark. I would like to start by asking one question. So in the last slide where you showed that there are 4 different kinds of problems that are being dealt in a university course scheduling, um, there's one square that was shown on revision. Could you give an example of uh, what what that entails, like some kind of problem that comes up in a revision? Because I guess that when you do a revision, you need to do a consistency check whether uh, it is still a consistent schedule. So if not, then what is the difference from consistency check?
Oh, Mark, you are muted.
Okay, so You picked a very interesting form of inference, revision inference. It's quite a challenging problem because, yes, you have to update the existing tables, but in such a way that both the new constraint and the old constraint can be satisfied. There is a trivial way to implement this. You could implement it using as a form of minimization inference, where you say, I will compute a new solution with a minimum number of changes compared to the existing solution that satisfies both the constraints and the new constraint. Does that make sense?
Yeah.
So you have a predicate, or you describe the link between the existing database and the new database, the new solution, using by describing what updates need to be taken. You delete certain facts, you add certain new facts, perhaps you modify certain facts, and you search for a solution of such an update which minimizes the set of updates. But so in the ultimate, that in the resulting database, all the constraints, the new and the old ones, are still satisfied. That's one way in which you can do it. Of course, that could be a very demanding inference problem. There are all kinds of heuristic ways. For example, you could search for small updates. So you could impose a constraint saying, I cannot use more than 5 updates, and then let the search engine search for suitable changes, and then increase your window to be able to find a good solution. But it's certainly a difficult problem. It's not a problem where our solvers are extremely fast in it. Okay. I only wanted to illustrate this principle that we want a knowledge base to be used for multiple forms of inference.
That makes sense.
Marc, I really enjoyed your presentation. I'm curious what you think of epistemic logic. Does it play a role in the type of system you're interested in building? Are there interesting questions around knowability that are worth formalizing in a system like this?
Well, that's also an excellent question. Well, it strikes me that in so many applications, the knowledge is really almost entirely objective. I don't know how you think about this, but if you want to model scheduling problems, constraint problems, very often the knowledge that you possess about these systems is objective, and there are only few cases that we have hit that require epistemic reasoning. Now, there are exceptions though, and maybe Simon can say a bit more about this, but one case that of course is quite frequently in the context of DMN. Are you familiar with the language DMN? Decision modeling support language?
I'm not.
You're not? Okay. So DMN is a kind of a base formalism used in business rules very often, where you describe decisions of certain problems. For example, you describe, using a number of rules, a set of decisions whether a client can get a reduction and how much the reduction will be. So depending on on the amount that he bought, on the products that he bought, on his age perhaps, you decide to give him a reduction rate. And special rule-based formalisms have been presented for that. Now, quite often, such a DMN application has to be executed in the context of incomplete knowledge. In that case, what people really need to take a decision is the decision rules become epistemic rules. For example, if you know that the agent is, or that the customer is less than 24 and you know that he is from the US, then even if you don't know the amount that he spent, you will give him a reduction. Things like this. So it's very well known that there are lots of problems with DMN to take decisions in the context of incomplete knowledge about the parameters of the decision problem. And there, epistemic operators will be really quite essential. So yeah, that is a certain application where epistemic operators are important. If you want, I can send you a reference about work that we've done about this.
Yeah, that would be awesome. I appreciate it. I'll share it in the Slack too for other members.
Okay. Other questions? Then no other questions. I'm really sorry again for having been carried away, especially to you, Simon. Sometimes it happens to me.
Mark, no worries at all. We'll schedule a follow-up event so Simone can present as well.
Okay, thank you. I'm grateful.
Well, thank you so much for talking to us today. We really appreciate it. And is it okay if we post the recording so people can listen or watch afterwards?
Sure.
Okay. And then Simone, I'll follow up with you and Mark afterward to organize a talk for you.
All right.
Perfect.
Okay.
So, thank
Thank you,
you.
everyone.
Thank you.